Hello, everybody. It is my pleasure to welcome you to today's ECD Star Introductory Colloquium on the science topics of the workshop, Key Reactions in Nuclear Astrophysics. This workshop was originally planned for 2020, but has been deferred to 2021 because of the COVID-19 pandemic. It will focus on nuclear reactions relevant in various astrophysical settings, such as stellar burning, core collapse supernovae, and neutron star mergers. The understanding of nuclear synthesis processes and of the energy generation in astrophysical environments requires dedicated experimental and theoretical studies on a large variety of nuclear reactions that are complemented by astronomy with observations in electromagnetic and also element abundances in the galaxy. As you know, the intention of these colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's talk will be given by Aurora Tumino. Since 2014, she is a professor of physics at the School of Engineering and Architecture at Aurora University in Enna in Italy. She is also an INFN researcher at the Laboratorio Nazionale del Sud in Catania. She got her graduate education at the University of Catania, receiving her PhD in 2020. After a one-year postdoc position at the Hahn-Meitner Institute in Berlin on a Humboldt Fellowship, she went back to Catania as a postdoc from 2001 to 2007, before taking a position at Aurora University in Enna. Her research activity is focused on topics related to nuclear astrophysics, in particular on the application of indirect techniques to study two-body reactions between charged particles at the sub-Coulomb area. She is serving on several advisory committees, among them the Institute of Nuclear Physics in Orsay and the Timber Labs in South Africa. She is also one of the editors of the European Journal of Physics A. For her work on carbon fusion, she has been awarded the 2019 Giovan Pietro Garibaldi Prize. Aurora, thanks very much for giving this talk.
Today, I'm going to discuss some of the topics of the workshop on key reactions in nuclear astrophysics that will be held at ECT Star next year, hopefully in presence. The workshop intends to discuss existing results in nuclear astrophysics and to identify key reactions for which the stable and radioactive beam facilities needed to assess information of interest for nuclear astrophysics. Before starting, I would like to say that I'm giving this colloquium also on behalf of the other organizers. And I want to warmly thank them also for the friendship and for the nice and joyful atmosphere in the organization of the workshop. I want to say also that I'm going to address the relevant points in a simple way for a broad audience to keep the spirit of the ECT Star colloquia. In the first part of my presentation, I will address nuclear astrophysics, giving an introduction, a short introduction. Then I will present a draft of the scientific program of the workshop. And in the second part, I will move to discuss the state of the art for some cases of study. So let's start. Nuclear astrophysics is considered at the crossroad of nuclear physics, astrophysics, and cosmology. And it was indeed introduced to try to answer fundamental questions such as what is the origin of the elements, how do stars and galaxies form and evolve, what powers the stars, how old is the universe. Of course, nuclear physics becomes a key ingredient in order to link the macrocosmos with the microcosmos. The publication year of the famous B2FH review paper is considered a kind of birth year of nuclear astrophysics, because this is one of the first times where we see clearly stated that nuclear reactions are responsible for both energy production and the creation of the elements in stars. And the authors highlight also four environments where nucleosynthesis takes place: the cosmological, the stellar, the explosive, and the galactic nucleosynthesis. So where we are 60 years after B2FH, we may say that we have a basic understanding of cosmic nucleosynthesis, although elemental abundance evolutions are not well described. And the astrophysical models for all sources are first order only, and upon a close look, inconsistencies and contradictions prevail. However, we are living a very nice era where increasing accuracy in the observations and also in nuclear physics experiments, of course, will help to tighter constraints the chemical evolution of the different sites. So I want to show this nice periodic table where basically we see what is our current belief in terms of nucleosynthetic source of elements in the solar system. And you also recognize that each element in the periodic table is color-coded by the relative contribution of the nucleosynthesis source, and these black elements are the lightest ones: hydrogen, deuterium, helium 3 and 4, and lithium, that have been formed during the Big Bang nucleosynthesis in the first 3 minutes after the Big Bang. Except for the beryllium and boron, the other elements are formed in stars and in several ways. Another way to show somehow our belief is so another way to show our current belief is through the abundance, showing the abundance of the elements, where you can easily recognize how huge is the abundance of hydrogen first and helium second with respect to the other elements. And as I mentioned, starting from carbon, the nucleosynthesis takes place in stars by build-up of alpha particles, and this happens up to iron. Iron is the element with the highest bonding energy, and after that, basically the star does not need any reaction, because somehow they are useless in terms of energy production. And all the other elements are produced through neutron capture, as we'll say later. And another nice feature that I want to underline is this alternatingly larger abundance of elements with even atomic number. And I want to stress here that indeed this spectrum is full of features and constraints coming from nuclear physics. And I would like to focus on nuclear physics, starting from the idea that nuclear reactions in stars produce energy and synthesize elements, of course. So the key parameter that nuclear physics provides is the stellar reaction rate. That comes from the product of the velocity distribution of nuclei in the plasma and the cross-section. The velocity distribution is usually described in terms of Maxwell-Boltzmann function, while for the cross-section there is no nuclear theory available to determine the reaction, so to determine this parameter a priori. Indeed, the cross-section depends on the properties of the nuclei which are involved and on the reaction mechanism. So what it is done is, it is usually a kind of joint adventure between experiments and theory in order to determine the stellar reaction rates. If one looks at the nuclear reactions between charged particles, of course, the main issue is the presence of the Coulomb barrier, because the energy available is really very tiny. It comes from the thermal motion, and for example, for our sun with an inner temperature of the order of 15 million Kelvin, KT is just of the order of 1 keV. So we are deeply below the Coulomb barrier, and this means that the reaction can occur only through the tunneling, so through the tunnel effect. And so the cross-section will be dominated by the tunneling probability that is usually described in terms of this exponential factor known as the gamma factor. So if one looks at the two ingredients to determine the relative probability, we see that we are basically with the convolution of the higher energy tail tunneling through the Coulomb barrier. And this convolution provides us with a gamma peak that nature gives us. And this is indeed the place where the measurements should be carried out. Indeed, a gamma peak is the most effective energy region for thermonuclear reactions to take place. And usually the energies within the gamma peak vary depending on the reaction and on the temperature. However, as you can see here in the table, usually these E0 are much below the Coulomb barrier. And again, just to stress that what I'm going to tell you is very sensitive to the Coulomb barrier. Indeed, also why the burning of the elements in the stars is taking place in separate stages is essentially due to the Coulomb barrier. So what people usually do, they try to measure the cross-section over as wide a range as possible, and then they extrapolate down to E0. And the extrapolation is done through the definition of the astrophysical factor, SE, which turns out to be a smoothly varying function of the energy than the cross-section. And basically because of this exponential factor, which is the inverse of the gamma factor that has been traditionally introduced in order to remove the bulk of the Coulomb barrier, or the Coulomb suppression. However, the extrapolation usually is a source of additional uncertainty because we go into an unknown region where unknown resonances might be present and also tails from subthreshold resonances. So how can we avoid extrapolation? We have to try to improve the signal-to-noise ratio. And I like to show this picture. You see a very crowded football stadium, probably during an Italian match. This is kind of picture which is not common in our strange times. However, we hope that in the future we are going to experience such a crowded field again. However, it is like we want to hear a little bird singing during a football match, a crowded football match. Of course, it's very challenging. So how to improve, to work on the signal-to-noise ratio? There have been several attempts. We can try to perform experiments for longer period, so increase the beam time. We can try to use pure targets, high beam currents, and to go underground to perform the experiments. And this is also a nice idea. So it is more than an idea. We have a nice laboratory also in between the Gran Sasso Mountain. And I would like indeed to show a very nice result from the Luna collaboration during the phase number 1 with a 50 kilovolt accelerator, where they investigated 2 important reactions in the solar PP chain, just two of them in 9 years of activity, because the signal to noise ratio is really very, very small. And in particular is on the left side. I'm showing you the result coming from a kind of breakthrough experiment, because they were able to show that there is no nuclear physics solution to the problem of the solar neutrino flux reduction. Indeed, it was expected to find a resonance in the gamma peak of the helium-3 plus helium-3 to P helium-4 reaction, but it was not observed. Indeed, from these first experiments, another important effect came out that basically due to this, to the increase of the cross-section of the S factor at low energy. And this effect is the electron screening. And you see this increase, this unusual increase of the S factor at low energy is basically due to the electrons surrounding the interacting ions that somehow partially screen the Coulomb repulsion. Of course, this is an effect which has to be removed from the data in order to assess the reaction rate correctly, because the screening in plasma, in the stellar plasma, is not the same as the one we experience in the laboratory. So we basically understood that there is no way to determine this parameter that we call the bare nucleus S factor from direct experiments at energies where the screening becomes important. And this is why indirect methods have been introduced in nuclear astrophysics. Indeed, they provide us with cross-sections at never reached energies where the signal is below current detection sensitivity. They also allow to get an independent information on the screening potential. Indeed, the screening story is somehow not understood well, because from the experimental activities that have been performed so far, it comes out that the screening potential is higher than the upper limits provided by atomic physics models. So something has to be still understood. And moreover, indirect methods, they allow to overcome difficulties in producing a beam or targets when radioactive ions and the neutrons are involved. So essentially, they provide us with quite straightforward experiments without Coulomb suppression, without electron screening. However, we have an important drawback, that the entrance channel and the exit one can be linked by several reaction mechanisms. So we need a reaction theory in order to select only the proper reaction mechanism. However, nowadays we have powerful techniques and observables to make a very careful data analysis and theoretical investigation. I want to mention some of them that have been used and are being used since 2 decades. The Coulomb dissociation in particular is very powerful to determine the absolute cross-section of radiative capture reactions, say capital A plus X going into B plus gamma. And this is done by studying the reversing photodisintegration process that is induced by the virtual gammas emitted by a very heavy targets. Then through the detailed balance, we can get back to the S factor for the radiative capture, of course, with the advantage to use thick targets and also to have a larger cross-section. That means higher rates. Of course, we may have some drawbacks coming from the contribution of the nuclear breakup if the energy of these gammas is large, or the contributions of other multiples. So one has to be careful. And this is the formula that connects the two cross sections, so that allows to get back to the cross section for the radiative capture reaction. Here, a short list of the early and forthcoming experiments. In particular, this method will be applied to the important reaction carbon-12 alpha gamma, and this will be discussed during the workshop. I move to the ANC. The ANC is another method to determine the zero energy S factor for a radiative capture reaction. Here, studying a peripheral transfer into a bound state of the B nucleus. So provided that the transfer is peripheral, the ANC that comes from the measurement of the cross-section for this process can be quite straightforwardly connected with the SE factor, with the cross-section for the radiative capture. The drawback here is that we require accurate optical model potentials. Otherwise, we have to make additional experiments. Also for this technique, here a list of early and recent experiments. I move to the Trojanus method that is applied to reactions between charged particles, and the idea is to determine the relevant low energy two-body cross-section by measuring the quasi-free contribution of an appropriate three-body reaction in a peculiar phase space where quasi-free kinematics rules. So if I focus on this 2 to 3 body process, peculiar means that either the target or the projectile, say this small a nucleus, is described in terms of two clusters, X and S, and if we select the quasi-free mechanism, we have this kind of mechanism that is shown in the cartoon here, where essentially this small a nucleus helps the X particle to overcome the repulsion wall, while the other cluster S remains spectator to the reaction. Of course, we have this diagram, which formally shows what's going on. And if the beam energy is chosen to be above the Coulomb barrier, this will provide us with this second vertex for the two-body reaction of interest to be without a Coulomb suppression and without electron screening. This formula allows us to determine the two-body cross-section of interest once we measure the cross-section of the 2 to 3 body reaction. However, let's say the main drawback of this theory is that we need the direct data to normalize the trend that we obtain with the Trojanus method. The method has been applied many times to more than 30 reactions, which are relevant for astrophysics, with very important results. So this is just the end of my first part, and here a draft of the scientific program of the workshop. We plan to have kind of such a kind of list of topics. We are going to discuss of cosmology and Big Bang nucleosynthesis, of hydrostatic and explosive nucleosynthesis, of neutrino and nucleus interaction, of nucleosynthesis in extreme environments. Of course, we will focus also on techniques, tools, and facilities for nuclear astrophysics, and on direct observations of astrophysical phenomena. Of course, the idea is to try to make a focus on key nuclear reactions important both for energy generation and nucleosynthesis in this variety of astrophysical sites. And of course, we will be guided by the beautiful sensitivity studies that we have in order to understand the role of these nuclear reactions and hopefully to identify new ones. So next, in the second part of this presentation, I want to focus on a few cases of study. In particular, I will say something on the cosmological lithium problem, on the hydrostatic nucleosynthesis in massive stars, to make a focus on helium and carbon burning, and on the complementary information that can come from gamma ray astronomy applied to aluminum 26 and iron 60. Then I will shortly discuss on the neutron sources in the SProcess. I will just mention the RProcess nucleosynthesis and nova and supernova nucleosynthesis. So the Big Bang nucleosynthesis was first proposed by Alfred and Gamow in 1948, and as I mentioned before, is responsible for the formation of lighter elements. The Big Bang nucleosynthesis didn't go beyond lithium because, first, because the nuclear physics, because of nuclear physics constraint, since we don't have stable nuclei of mass number 5 or 8, but also because of the decreasing in temperature due to the rapid expansion of the universe. However, the model of Big Bang nucleosynthesis can predict the abundances of these light elements using as inputs the cross-sections of 12 key reactions that are listed here, the baryon to photon ratio, and this is the number coming from WMAP, and the neutron lifetime, which is a puzzle itself, but I'm not going to discuss about that. So once we have these abundances, we can check if these numbers are comparable, agree with the observations that have been performed in all the parts of the universe, such as metal, poor halo stars, and globular clusters. And the result we get is this nice spectrum where the green areas come from observations, the blue and the red lines show the calculations. And so if we just neglected helium-3 because it's hard to measure since most stars burn it, we have for the other abundances agreement except for lithium-7. And this is what constitutes the so-called cosmological lithium problem. So how to proceed? Of course, people are working quite hard in order to solve this cosmological lithium problem. And we can improve cross-sections of the network reactions. We can also improve observations with unexplored areas. But of course, we can also introduce a new physics. In particular, from the nuclear physics point of view, people are discussing about the role of the primordial beryllium-7 that decays. It's a source of lithium-7, but if it is destroyed, of course, this will go into the direction to have less lithium-7. And the main reactions destroying beryllium-7 are those listed here on the right-hand side, and these will add to the network of key reactions for the Big Bang nucleosynthesis. It has been already a lot of work done, and other experimental activities is ongoing. And I'm going to show you here these two spectra. This on the left-hand side comes from a nice experiment of the Entov collaboration, where they could provide the data up to 1 kV, but they are just at the beginning of the energy region of relevance for the Big Bang nucleosynthesis. Nice results came from other measurements, and I want to highlight a nice result coming from the Trojanus method application to the beryllium-7 and alpha helium-4. And here it is shown as black and blue symbols. Of course, the error bars are somehow still large. Other experiments will be performed in the future, but of course they already give us an idea about the cross-section. Of course, these numbers have to join the other numbers coming from the other reactions in order to make an important statement for the cosmological lithium problem. There have been other original and non-nuclear solutions, like the decay, the WIMPs decay, or the decay of JeV scale SUSY particles. And nicely also the need of introducing new statistics to describe the velocity of nucleons during the Big Bang nucleosynthesis era. So a lot of activity is ongoing, and some of them, of course, will be presented during the workshop. I move to the hydrostatic burning of a massive star. Of course, its life starts like our sun. So we have the main sequence where the hydrogen is burning in the core. After that, the core collapses and starts another stage, the helium burning stage. And after that, a massive star experiences another core collapse, and it gets hot enough to burn carbon and oxygen. And after that, other stages, of course, will proceed till the structure will have iron in the core, an inert iron in the core. Because as I said before, iron is the element with the highest binding energy, and reactions after iron will not provide energy to the star, so they will not help the star to stay alive. And after this nucleosynthetic process, we see that the massive star becomes kind of onion with all these layers showing the heavier element, the lighter elements. Okay, so the massive star, of course, has a quite complex interior, and the different reactions they contribute, and in particular the helium burning stage is a very affecting, very important stage for the evolution of a star. It is a kind of two-stage process. The first one is the triple alpha process that produces carbon, and whose rate is known to 10% uncertainty. And the second stage destroys helium, and it's the carbon-12, the famous carbon-12 alpha gamma reaction that is considered a kind of holy grail for nuclear physics, but unfortunately is quite poorly known. Indeed, as you can see from this picture, the gamma peak is where this question mark is, so around 300 kV, but the cross-section here is the result of interferences between resonances and non-resonant components. So this makes it very difficult to determine the cross-section of this reaction. And however, the competition of these two channels is very important to determine the carbon over oxygen ratio in the universe, which is a very important parameter to constrain the stellar evolution of massive stars. So among the forthcoming tries in order to tackle this cross-section, we have the beta decay of nitrogen-16. We have the use of intense gamma beams delivered on oxygen-16, so which is the inverse of the photo of the capture, and the Coulomb dissociation. And out of nuclear physics, there is a nice attempt to infer directly the carbon over oxygen ratio from white dwarf seismology. Of course, some of these topics will be highlighted during the workshop, and there will be at least one dedicated session to the nucleosynthesis in helium burning. I go to the carbon burning. So the carbon burning is another crucial phase in the nucleosynthesis of massive stars because it affects their later stellar evolution. It determines also the so-called M-up, which is a mass threshold for the hydrostatic carbon burning. But it seems also to play an important role in the ignition conditions for superbursts and type 1a supernovae. So the main channels are these two, these are the alpha and proton channels, at least below 2 MeV. And so the astrophysical region of interest goes from 1 to 3 MeV. And unfortunately, from direct measurements, the minimum energy is 2.1 MeV, and any further experiments below 2 MeV is extremely challenging because of this rapid decrease of the cross-section. There have been many tries to extrapolate the behavior, but as you can see here, these lines, somehow they differ by several orders of magnitudes, and they do not consider also the presence of resonances in the low-lying region. A couple of years ago, we have published a very important paper related to our results with the Trojanus Method, where we were able to span all the astrophysical region down to 1 MeV, and we saw very clear signatures of resonances in these low-lying regions. So we were able to determine the total reaction rate that is of importance, of interest for stellar models. Now, what comes next? We hope that from direct experiments, we can have additional data below 2 MeV, and people are putting a lot of efforts on that. I'm just mentioning the stellar collaboration and the Luna megavolt process. And from, let's say, indirect point of view, what we want to do is that since I told you that the main drawback of the theory is that we need direct data for the normalization, we will try to improve the normalization of the Trojanus data to have also a larger overlap with direct data. But the reaction rate is there. So just to mention that, of course, there are other reactions that may affect the stellar interior. And so we can learn a lot, in particular, on the nuclear reactions to produce aluminum-26 and iron-60. However, their nucleosynthesis paths are still still quite uncertain because affected by very large uncertainties. But I want to just to focus on the complementary information that can come from gamma ray astronomy. And indeed, this is a beautiful spectrum coming after more than 5 years of observation. This is the signature coming from the decay of aluminum 26 in our galaxy, and was taken using the Compton telescope and the Spion Integral. And recently there was another important result coming from after 15 years of data taking. And you see here this spectrum showing the joint observation of the gamma ray characteristic of aluminum 26 decay and the two lines coming from the decay of iron 60. Indeed, the joint observation of these lines is a very good discriminant of different sources that are generating aluminum 26, because it seems that these two isotopes are produced in the same regions in the massive star and roughly in comparable amounts. So in this experiment, in this nice paper, they were able to also to give an estimate of the flux ratio, and this is going to have strong implications for massive star models and their nucleosynthesis. So I moved to the synthesis of the heavy elements, making a focus on the SProcess neutron sources. So the SProcess, where S means slow, is responsible for about 50% of the nuclei heavier than iron, in a time scale, a huge time scale between 1,000 and 10,000 years. Of course, important inputs for the SProcess nucleosynthesis models are the main neutron sources, namely the carbon-13 alpha N and the neon-22 alpha N. The carbon-13 alpha N takes place in the helium layers, burning layers in low-mass AGB stars, and it is responsible for the production. So it is the source for the so-called main SProcess, responsible for the production of nuclei with A larger than 90. Of course, the knowledge of its cross-section is extremely important. And as you see in this nice spectrum, the relevant region that is around 190 kb is not reached by direct experiments. So these symbols, colored symbols, show the contribution from direct experiments. So up to now, no way to go below 200 kb. So we know this region just from indirect measurements, and this is a nice experiment that has been performed with the Trojanus method. Of course, there have been other indirect measurements, and somehow they are going to have a kind of joint consensus. The situation for the neon-22 alpha N is a bit worse, because so first, the neon-22 alpha N takes place during helium and carbon burning in intermediate mass and massive stars, is the source for the weak SProcess that provides nucleids with A between 60 and 90, and it is still largely unknown. Direct experiments stop at 800 kb. They show the presence of this resonance, but in this low-lying region, which is basically the gamma window, the information comes only from theoretical calculation and from spectroscopy studies that provide only upper limits. So the situation is still, people are working in order to seize. I move to the R process. The R process, where R means rapid, is responsible for almost the other 50% production of heavy elements. The time scale is completely different, is of the order of, let's say, less than 1 second. And for this process, high temperatures and high neutron densities are required. The idea is to add neutrons very rapidly before nuclei have the time to beta decay, and after a while we reach the so-called waiting point nucleus, where that is essentially a nucleus unstable to beta decay. And after the beta decay, the new nucleus will have a new neutron drip line, and in most cases will be able to capture more neutrons. So the R process is still, so we don't know exactly where it occurs. There are, of course, gases and some experimental evidences. People are discussing whether the hot bubble just inside a supernova shock can be the right site, or after the observations of the mergers 3 years ago, they're also considering fusion of two neutron stars. So a neutron star and black hole, these mergers should be sources for the R processes. Of course, in both cases, if we say, oh, there are some issues. In particular, in the first case, it is not just justified the very low abundance of R process nuclei in interstellar gas, while in the second situation, the time scale is still a problem, and it seems that only this source, so the nucleosynthesis in the mergers, is not enough for some elements. However, very recent results, also from the observation of the europium abundance, they point to a joint contribution for the R process, so two distinct sources of the R processes. However, it is very important to understand the R process in order to tackle the abundance of the elements in the universe. And models are very sensitive to neutron capture rates, to the beta decay properties, to the fission barriers, and to mass measurements. And you see from this figure that still there is disagreement between observations and calculations, and basically because also these calculations are let's say, based on nuclear physics knowledge coming from stable nuclei. So maybe something has to be revised also in terms of nuclear physics. By the way, we need a lot of experimental activity in this field, and the problem is also that the D gamma reactions are quite challenging in the lab. However, so in spite of being very challenging, we have at least a couple of choices. We can study the N gamma, creating radioactive ion beams of these short-lived nuclei, and deliver them on deuteron targets. So the deuteron will become our virtual neutron source. In this case, we apply a technique that is called the surrogate reaction technique, or we can also apply the Trojanus Method, which is basically very similar to the surrogate reaction technique, but in a peculiar phase space region, as I mentioned before. There is another nice idea, very recent, to produce a neutron target from a spallation source of protons and tungsten, in a way to destroy nuclei and evaporate neutrons. Neutrons are after that thermalized and can be used as target in storage rings that are used in order to increase the intensities of these radioactive nuclei. So people are working, and there is a lot of really lot of new ideas. Here, just an example of beams from fragmentation facilities that have the advantage of using beams of mixed nuclides, and they also provide fast identification on event-by-event basis. Of course, the hope is that in next year, all the laboratories in the world will be able to cover a large part of the RProcess path. Okay, so very shortly, since my time is almost over, I want to just to say a few words on the nucleosynthesis in classical and recurrent novae. I want to say that the observations also for this site, for this environment, are higher than model predictions, and so it is pointed to a problem with either the models or the nuclear physics inputs. People are working a lot. They providing these sensitivity studies to guide the experimental activity. In this work, they were able to put a huge number of nuclear reactions in the network calculations, as you see here. However, there are some of these nuclear reactions that are the source of, so that where the main nuclear uncertainties come. In particular, I'm highlighting here 3 of them: the fluorine 18P alpha oxygen 15, the aluminum 25P gamma, and the phosphor P gamma. And there is a lot of activity for these 3 reactions since already several years. And of course, they will be discussed during the workshop. A similar situation applies also for the nucleosynthesis in type 1a supernovae. Again, here we have several sensitivity studies to guide the experimental activity, and again we find that the abundance pattern of the ejecta is not reproduced by models. So again, we have to work on the field. And I want to finish with this chart of nuclides, just to show, to highlight the huge activity that is being performed in order to provide what are the nuclear data needs. We need the masses, we need the beta decay rates, and we need the reaction rates. Reaction rates that, of course, can be provided through direct measurements as well as in the indirect approach. Okay, so I think that, of course, this is just a taste of the topics. Much remains to say, and I hope that we can discuss, of course, in person. I want just to say that we are proud and honored that more than 50 colleagues accepted our invitation to be speakers at our workshop. And we hope to see them and to enjoy their presentations in person. Thank you very much.